Okay, so for the third talk, we have Yuyu Mo. Tell us about Mellin momentum amplitudes.
Okay, yeah, thank you. Yeah, thank you for the organizer for giving me this opportunity for this talk. So today I'm going to talk about, as Sean just said, Mellin momentum amplitude and on-shell bootstrapping ADS. So this is a work based on original idea from Jiajie and our collaboration for 5 graviton. And later we developed our formalism for soft theorem or for soft limit with Chanja and Asa, who is also the co-host here. Okay, so how do I change?
Just right or left.
Right or left?
Oh, sorry.
I cannot change.
Could you try now? Okay.
Okay. Yeah. Sorry about that. Okay. So let's move on. So the first thing to want to say is the motivation why we need on-shell bootstrap in computing all these physical quantities. So first of all, we know that in usual textbook method that we write down our Lagrangian based on the physical principles such as causality, locality, and unitarity, and then we compute our observable based on the Feynman like the amplitude or correlator based on the Feynman diagram that we written down according to our Lagrangian. And this usual textbook way is very important, of course, in computing many important original works like Gaussian, non-Gaussianity or other important computation. Well, however, if we want to go to higher points for these correlators or amplitude, especially for gauge theory amplitude, it is not quite efficient. For example, if you compute a 4 graviton amplitude in flat space, that if you sum over all this Feynman diagram, each diagram contains hundreds of thousands of terms. Well, in this approach, why we have such terms? Because when we compute Feynman diagram, the diagram treats all these external legs as off-shells, and in this off-shell, it's not gauging. It's highly gauge dependent, and it's contain many gauge redundancies. So we basically sum over 0 plus 0. So the way to speed up the process of computing such as tree-level gauge theory amplitude at higher point is to use the amplitude bootstrap technique that we basically just by requiring the consistency condition of the physical principles such as this thing listed here to directly constrain our observable such as amplitude and correlators by requiring the consistency relation between these. And moreover, this can even, like at tree level, this can even fix the amplitude directly. For example, if we do the same thing for the 4 graviton scattering in flat space, then using amplitude bootstrap, this just gives me that this amplitude in this given Helicity configuration is just this one term here. And we can go further, and this bootstrap story tells us that if the only low energy effective theory that satisfy the Lorentz symmetry, unitarity, and locality is the Einstein gravity for these spin tube particles. And this is very remarkable for using the bootstrap idea to understand the Einstein gravity in flat space. And now the next question to ask is, what about curved space? Especially nowadays for phenomenological purpose, that what about in cosmological background or black hole background? Can we do amplitude bootstrap in this background? Okay. So the object that we're working on is to basically we use ADS-CFT as a playground. That we know the observable for this ADS is the boundary CFT correlator, and it's basically computing by using a differential operator acting on this contact diagram where you integrate your bulk-to-boundary propagator by this ADS bulk directions. However, the reason that we didn't working at CFT correlator is because this correlator is not invariant under field redefinition because of these local terms here, and it's also not invariant under the shift symmetry or under the symmetry transformation, such as shift symmetry or conformal word identities, such as here. So, but as we know, in flat space, we don't have these problems because we have S0 reduction formula for the amplitude, and we take each leg on shells. So the treatment for this problem is to use Schaller and Massimo's idea, and as pointed out by Javier, that we can just do a Maulin transformation for the Box-to-boundary propagator. And then why we want to do that? Because we know the Box-to-boundary propagator satisfies the equation of motion, the Klein-Gordon equation in the ADS. And then this turns this equation to an on-shell condition for each external legs, just like k squared plus m squared equals 0 for the amplitude in flat space. So with this on-shell condition, if we want to use that for our computation, then the natural object you're working on is this curly A here, what we call Maulin momentum amplitude. After this definition, we find that this object has no local terms and is exactly invariant under Fourier definition or other symmetry transformations. Okay, so this is a unique object. So the uniqueness of this thing help us to bootstrap higher point amplitudes and also higher point correlators. The correlator is just related to the amplitude up to this final Box-to-boundary integration. Okay, if we first integrate out this ds, and then it's just like usual how we just like usually how we compute the Witten diagram. Okay, so just as the usual, like we heard a lot of talks about defining amplitude in ADS these days. So if we want to define an amplitude-like objects, though the flat-based limit of these must be reduced to flat-based amplitudes, and if under this map, you can just show that if we take z goes to infinity, this will just reduce to flat-based amplitude. So here is the table comparing the flat-based amplitude we know and loving, and also the Maulin momentum amplitude. So this is the symmetry groups that they are invariant. And under this translation, you can see that there is the delta function. The dilatation symmetry tells us there's also a delta function for this Merlin variable. Basically, just integrate out the z direction, and this Merlin kernel will just give you this delta function. So in flat-based limit, you can see that if we take z goes to infinity, this little z here is too small. If you take z goes to infinity, this just becomes the energy conservation condition for here. Here's d plus 1, here's d. And then the other, as we just introduced, this Maulin momentum amplitude has the same on-shell condition. For each leg, you will have an on-shell condition, just as flat space. And these are the post structure. So this is the 1 over the curly d, which is the 1 over the Klein-Gordon operator. And if you take the flat space limit, just as Raman's talk, you will just reduce to usual the 1 over this Mandelstein invariant in flat space. Okay, I will talk about this post structure later, just in next slides. So as an example of this Maulin momentum amplitude, you can write down the Feynman rule for some fairly simple theory as compared to gravity. You can write down a Feynman rule for gluon in ADS, and the Feynman rule is just like the flat space, but now you just replace your zeros component of the energy to be this Maulin variable, and the propagation is like that. This is the inverse equation of operator, which acting on some function gives you the convolution of the function with the Green's function with the Box-to-Box propagator, and this is the OPE pole that we will give some more insight of this propagation later. Okay, so this is the thing. This is the usual way. We can write down the Feynman rule for a simple theory. What about gravity? We know gravity in flat space, the 3-point diagram, it contains 100 terms, and 4-point contains thousands of terms. So it's hard to actually compute graviton amplitude using directly Feynman rule. So the way to get through this process is just as what we begin, just use the Feynman amplitude bootstrap techniques. So we start with 3-point Merlin momentum amplitude for Young-Mills or general relativity. Then we require 3 constraints for amplitude. The first constraint is the unitarity. So it's just saying that in the pole of this 1 over curly d, which is the equation Klein-Gordon operator for anti-de Sitter space, then on the pole, the amplitude should factorize to lower point Maulin momentum amplitude that we derived earlier. And then the second condition is the variation of OPE limit, that on the operational product expansion limit when two sets of operator being far separated, that this on the residue the amplitude must be 0, And this is the second condition. And then the third condition just as we introduced just now, that the flat space limit, our Mauli moment amplitude must be reduced to flat space amplitude that we know and love. And it will restore the Lorentz symmetry after ignoring the curvature corrections. Okay. So with this preparation, we can do a simple example of the bootstrap. Okay, so onshore bootstrap. So we start with a 3-point gluon amplitude. If you can remember, in flat space, it contains 3 terms: epsilon 1, epsilon 2. Okay, yeah, k dot epsilon. You can use unitarity to bootstrap this term, and then by requiring vanishing residue in OP limit, you can, based on that, bootstrap this green term here. All these two give us the propagation of 4 gluon in ADS. And then the flat space limit, if you just compare our amplitude with flat space result, this just gives us the contact interaction as onshore bootstrap. Okay. So all these 3 just fix the 4 gluon amplitude in here. And you can also go back to the momentum space. You can also go back to boundary correlator space by just finishing the bulk integration. Okay. So all this process can be iterated, and you can get 5 Yang-Mills amplitude using the onshore bootstrap. Just use the first 2, and then all the way to endpoint in principle. So this basically just show the power of this onshore bootstrap. It's like a recursion, and then the power of this can not only restrict to Yang-Mills field theory, but it can also be gravity. So we can start with a 3-grain gravity onshore amplitude and bootstrap the 4-point using this consistent requirement of these rules, and all the way to 5-point and in principle endpoints. Then use the final scalar integration. You can just get back to the usual correlators that is between graviton on the boundaries. So this gives the first graviton, 5 graviton Merlin moment amplitude in this paper, and you can also go back to the momentum space and give you the first 5 graviton full correlators. Okay, so to demonstrate the power, there's another thing that we can bootstrap, which is to study the endpoint structure of the correlator and from this Merlin moment amplitude. So using the onshore bootstrap, we can just directly get the first term. Oh, basically, sorry, I have to say. So this is the diagrammatically soft limit that we study in our paper, and this is basically you glue a 3-point vertex with the endpoint correlator or endpoint Merlin moment amplitude here, and then you just study the soft limit if we take one of the leg of this 3-point vertex to being soft. And basically you use unitarity, you can fix the first term, and if you know this map, which is given here, the first term is exactly the one-block soft term, just as the previous talk. And the second term is requirement that add up these 2, you will get vanishing contribution. You will get vanishing residue in OP limit. So this is just, if you're requiring the OP limit constraint to satisfy, then you will get these second terms. And similarly for the gravity one. So maybe this doesn't look familiar to you. And if you go back to momentum space, then these basically bootstrap the relation between the m+1 point correlation function and with m point correlation function. The first one-block soft term just give you, if you compare the result, you just give you energy derivative acting on the hard legs. And the second term is basically like a gauge transformation term. You basically replace this epsilon on your usual correlator by this 3-point moment, by this boundary momentum. This is like a gauge transformation term. Actually, if you know this relation here, then you can rewrite your result. For example, the gravity result. Then you see that if you are familiar with cosmological context, this just looks like a consistency relation. And of course, we are trying to understand one interesting problem to understand these results is to see whether there is how to connect with consistent relation that is derived in cosmological or inflational context. And also, and we know that in cosmology, they derive the consistent result basically from word identity. As I'm sure some of the authors here knows this, and also derive this. And so basically, how to understand this result from geometrical perspective for like understanding from large gauge transformation or space-time symmetries. such as lambda BMS in ADS, which is analogous of BMS, as we heard a lot of talks in these days, which derive the soft theorem, usual soft theorem for soft limits, or for flat space limits. Okay, and basically this is our, and basically you can also use this soft theorem to bootstrap the Marlin momentum amplitude. So basically we check our results, like on this hard pole, and also the pole here, which is the energy square pole. And actually, this relation, we can also serve as a consistent check for our 5-going Young-Mills and graviton amplitudes. And we check it. Okay. So I think this is the final thing I want to say. Okay. Yeah. So here just the conclusion. And so we basically introduce the Marlin momentum formalism, which make use of this on-shell condition and also LSZ. This allows us to basically bootstrap the higher point boundary correlators. The correlator doesn't have to be a CFD correlator. It can also be a correlator in the theta background. Then to demonstrate the power, we use this bootstrap technique to bootstrap 5-point graviton amplitude and just also see the endpoint structures. Also, we basically bootstrap out the soft theorem for Young-Mills and GR, and without relying on space-time symmetry. So because of that, we can basically see how to, a possibility to go further is to extrapolate this formalism to FRW or black hole background in structure. And also, just as the amplitude cosmologist dream, that we can try to see if we can write Park-Taylor amplitude for these any de Sitter or de Sitter space. Yeah, okay, so that's all I want to say. Thank you. Yeah.
Have you written the 5-point amplitude of gravitons in Marlin space in one of your slides?
Yes. Yeah, here.
But an explicit expression in terms of the
Marlin momentum and also the boundary momentum. Yes. It's like 5. It's in computer actually. It's not quite short.
It's written in this paper.
Yeah. Well, we will give some details in the upcoming paper, but in this paper we haven't we already computed out the amplitude, but it's a short paper, so we didn't put it on. We didn't put the expression on the paper. It's very long. Yeah. It contains 15 channels, and each channel contains OPE and some 1 over curly D terms. Yes, but we check various limits. Yeah, it satisfies the consistency check. Yes.
Hi, you said like the soft limits 2, on the soft limits 2 slide, you said it's like a gauge transformation?
Yes.
So I'm not quite understanding. You mean to say that you just expand the polarization and that's why you're calling it a gauge transformation, or is there some other reason why you're calling it?
Because this term is like we replace your polarization for hard legs and replace that with a boundary momentum. So it's like a gauge transformation in this sense.
So what's the status of the gauge invariance of this object then?
Okay, that's a very good question. So the gauge transformation in the gauge that we choose, there's no gauge freedom. So the only thing that you do gauge transformation is through the special conformal word identity. Is you act on the special conformal word identity, just as in Bauman's paper. Yeah.
Okay. Any other questions or comments?
Just a really quick question and a naive question. You mentioned this awesome goal of trying to find something like the Park-Taylor formula in ADS, but even at low numbers of points, like 4 points, do you see any simplification for certain helicity configurations that would be the kind of hallmark of such a formula?
Yeah, we have been trying to use the boundary spinners as defined by Madasina and communities, and we can. Yeah, there is for example this 4-point Young-Mills velocity. Yeah, this 4-point Young-Mills result written in this polarization and epsilon dot case is very long, but we can basically simplify using the boundary spinor helicity variables by manifesting the flat space structure. Because what do we mean? We just identify a blob, which is quite short, that is vanishing on flat space limit, and the other one, what I mean, we compute a given configuration of O plus for this amplitude. We found that it can simplify a bit, but to write a Park-Taylor formula, first of all, there is you see this 1 over curly D here. If you have S channel, it's like that, and you have T channel, you have a completely different 1 over curly D, which is a differential operator acting on something. So you cannot be treated as a flat space like a Mandelstam, like just algebraic stuff. I've been recently discovered this also, and maybe a recent paper by Baumann, they used the twistor technology to encode the special conformal transformation, to manifest the special conformal and also current conservation. In this sense, maybe we can use that to basically help us to get rid of this 1 over curly D, which is you have many 1 over curly D in higher point, and there are many channels. I think in this sense we can use the twistor technologies to basically simplify the expression, and try to see if we can really write down a Park-Taylor. Thanks. Thank you.
Okay, maybe with let's thank the speaker again.
Okay.